Welcome back to Nature of Code in Rust and GGEZ. We're going to be going through example 2.2, forces acting on many objects. The example that we see here in p5.js is we're going to have a bunch of these movers in some kind of vector. They're all going to have different masses, and we're going to tie those masses directly to the size of the mover. Then we're going to apply the same wind force and the same gravity force as before to all of these movers. And everything else is pretty much going to be the same. The big things that we're going to change here is looks like we're going to have an alpha for all of the movers so we can see them through each other. So that would be a bit more interesting. We can also add like sort of an outside circle, white circle, and make them gray. That should make it a little bit nicer on the eyes as well. So let's go ahead and get into it. All right, so the first thing, we need to create a whole bunch of these. So let's head into the main library and set ourselves up for movers, which will be a vec of mover. Which means we need to set this up here. So that movers is use the macro to create a new vector, and then movers. Okay. So that sets ourselves up there. And if we want to create a whole bunch of them just right now, although I want to wait just a little bit because we might be changing movers in order to help us out. That being said, we do have some errors down here, so we need to make sure we're actually doing the thing to all the movers instead of just trying to access only one of them. So we remember how to do this. We're gonna self.movers. We're gonna get an iterator. If we notice, none of these need mutable access. So just a normal iterator. Is that true? No, we do need iter mute. We don't need to try. The for each, we can just do a normal for each. We're gonna get a mover. Then this down below here, and remove the self on here. That's not what we want. We want something like this. Okay, have all the self movers, apply this force, and we're done here. Same thing for down here. We're going to do a self.movers. This can be just an iter, but we have to do a try for each. We get a mover. We don't need that. All we need. Cut you out. Put you right here, and then we can put our question mark here. Okay, so, right, and no self.mover. There we go. Now, we have a problem here. It's telling us cannot borrow self as immutable because it's also borrowed as mutable. So the borrow checker is not a little bit not happy with us. And that's because we're taking our self wind force and we're moving it in over and over and over again, which is trying to take ownership of this. So there's a couple things we can do. First of all, let's change apply force to take in a reference to a force as opposed to an actual force. So to dereference it to force the copy, we'll just add a star here. And then we can use a reference here. However, that's not everything that we need to do. Unfortunately, because we're still having self-reference directly in here, it's still unhappy. What if things change? So we can actually extract out the wind force and gravity force and still have a reference to it up above here. And that's what the our pair programmer in the borrow checker is trying to get us to do. So we'll let wind force is equal to a reference to self dot wind force. Gravity force is a reference to self gravity force. If we do that, then we can then just reference wind force and gravity force directly. And that's it. No more errors. Now the borrow checker is happy with us and we don't have to give anything up really. All right, well that's to get one mover out. And if we run this now, everything should still work with the same single mover that we have before. Except it doesn't. What's going on with this? So let's see. Oh, you know why? Because we don't have any movers inside this vector. So let's go ahead and just put our one mover inside of here. So create our one mover, and let's try this again. And here's our one mover, and everything works the same way that it did before. Now, something we want to do is take our mass and have it apply to the mover directly. So if we go back into our mover, when we create a new one, I want our radius to be tied to the mass. So we can just have it be a 1-to-1 ratio. We can just do our radius is equal to the mass. That will copy over. And so now suddenly it'll become larger or smaller. And everything else I think is going to be the same, although I think we want to change the color a little bit too. So let's actually set ourselves a color. Color new. So, we can still make it grayscale, just plenty bright. 1.0 all across for RGB would be white. So let's do something like 0.9. And let's have the alpha be really close to being bright. So that could be maybe a 0.5, like just halfway. And then this color, instead of white, we can make you the color. We can also do a white circle around the edge of it. So do another dot circle, draw mode. This will be not a fill, but rather a stroke. We'll make this 2.0. Our same point is going to be exactly the same. 0, 0. The radius will be the same. Tolerance will be the same. But this time we'll make the color white. And that should work out for us. Let's go ahead and run this again, and we should see our update to the actual display. There we go. We have our outline, and it's nice and gray. Okay, that looks fine. Now, if we want to have a whole bunch of these and give ourselves a random number generator with it, I'm thinking something that I've been thinking about a lot recently is putting our random number stuff inside of a wrapper, basically using something similar to the adapter pattern, the facade pattern, something like that allows us to basically take control and make working with random numbers a little bit easier, especially if we want to change what kind of random number algorithm or crate to use. So in utilities, I'm going to create a new file called random. Head into mod and make Rust aware of this. All right, so we're going to have a pub struct random. For right now, we're going to store RNG. So this is going to be our random number generator. That's going to be our thread RNG. We're going to impl random. Now, something I've noticed is that RNG actually implements default. And we're going to get, like, Clippy is going to tell us, hey, we don't have to implement new ourselves if whatever we're trying to do implements default. I'll show you what I mean by that. If we have a pub function new here, and we're just returning a self, let RNG equals a thread RNG, turn a self with RNG inside. If I hit save on this, we get a warning. And this is, I believe, Clippy telling, yeah, it's Clippy saying, hey, we should add a default implementation for this. Okay, well, if I just come up and let's do a derive default. If I hit save, there's no errors. There is a default, which means if this is all I'm doing, I can just replace it. Like we could still have a new function, but instead of like actually doing the work now, we can just say self default. And that's what we're going to return. So a little bit easier for us, which means I don't need to pull in thread RNG because default's going to do that for us. All right, well, let's say I want to get a random range because that's kind of what we want to expose here in this. In this case, it's more of the facade pattern so far, but it might be adapter pattern, it might be another pattern that I'm not really thinking of, or like a combination of multiple of them. Let's have a pub function range. This is going to give us a range of random numbers between, like, let's see, we need a mutable self, min of f32, and max f32, and we're going to return an f32. Having it set for this f32 is going to make it a little bit easier on us whenever we want to pull in gen range too. We can actually write documentation for this as well, which will be available to us in our tooling when we try to use this function. So generate a random number between min and max exclusively. So we're not, like, if we want a number between 0 and 10, we'll get a number between 0 and 9.999 repeating. All right, so to get this, do self.rng, get our gen range, and then we have a range that's going to be min max. And that's it. We don't have to tell it what type to use because it knows it has to be an F32. All right, let's head back to the main library and use this. So when we're creating our movers, let's do mute random. And this equals utilities random new. And so we're going to want to loop through however many of these movers we want. In the book, it mentions having 100 of them. I'm not completely sure that's how many we have in that P5 example, but let's do 100. So I don't care about like the count of these. In 0.100, we want to create a new mover. So let's put this code down here. This also means we can't actually reference that yet. All right, so we have a new mover. Let's not make this start at the far left. Let's actually have it go over a little bit to the right. And then we also need to create the mass. And so if we remember, the mass and the size are tied together. So I want, let's see, let our mass is going to be our random dot range. And we see here's our documentation for that. We have our min or max. So let's say that we don't want anything smaller than a 10. And we don't want anything larger than a, I don't know, 35. That creates our mass. We can use that right here. For the x, we know that our radius is set to whatever this mass is. So let's do maybe our mass times 2 here for moving over to the right. So it's just on the edge of the left-hand screen. And height, we can also just do mass times 2. That way it'll be in the top left corner, no matter what our mass is. We have our mass, we have our context. That gives us this mover, and then we can do movers, push our mover inside. And then we should be happy. We don't need this, the width and the height anymore, at least in this location. And I think we're good to go. Let's go ahead and run this and see what it looks like. Cargo run. And there's all of our balls. and they're all moving at different rates, even though they're having the same wind and gravity applied to them. And that's just because of the mass difference. We don't have to make them all the same size. And the book does go into, in reality, you can have things that have a bigger mass, even if they're smaller objects. And even though they're not that's not necessarily tied to weight, it sometimes is. But in this case, I think it's a nice visualization of the different masses. The larger objects take longer to sort of move around. The smaller objects are zipping around. And that's it. That is example 2.2, forces acting on many objects. Thank you so much for watching, and I'll see you in the next video. Bye.